Dear ladies and gentlemen, hello everyone. Welcome to our second edition of NexFrontier on novel materials discovery, the marvel of computational science. My name is Felix Mösner. I'm the CEO of SwissNex in China, the science consulate of Switzerland in China. SwissNex is here to show the best of Switzerland, build bridges and connect with China in education, research and innovation. Situated in the middle of Europe, Switzerland is a landlocked country with no natural resources. This is why we have to continuously invest in brains, produce innovative solutions, and explore new frontiers, as we do with NexFrontiers. Today, we will learn about the role of computational science in the discovery of new materials and the application in electronics, energy, chemistry, medicine, and beyond. We are very privileged and delighted to have invited prominent speakers from the Swiss National Center of Competence in Research on Computational Design and Discovery of Novel Materials, the NCCR Marvel and EPFL, then Fudan University and Beihang University. This NexFrontier series is the latest webinar series at SwissNex in China, which spotlights cutting-edge research in Switzerland and China with a focus on Swiss National Centers of Competence in Research, the NCCRs, and top-class research institutions in China. The aim is to spark potential exchanges and future collaborations. I would like to thank Libing, Lefei, Sherry, and my whole team at SwissNex for the excellent job during the past weeks. Lefei, the floor is yours. Thank you.
Thank you, Felix. Good morning and good afternoon, everyone. My name is Lefei Chen. I'm a junior project manager for academic relations at SwissNex in China. Before we start, a kind reminder to our audience. At the bottom of the Zoom interface, you can find the Q&A function. Please type in your questions during the webinar and we will answer them in the Q&A session. Now, I would like to introduce our first speaker, Professor Nicola Mazzari. He holds the Chair of Theory and Assimilation of Materials at EPFL, where he is also the Director of NCCR Marvel. He also currently holds the Excellence Chair at the University of Bremen. Professor Mazzari, the floor is yours.
Thank In particular, thank SwissNex for organizing this and Professor Clemence Comminboeuf at EPFL, like me, and Professor Xingao Gong and Kobe Wang at Fudan University at Beiyang for joining us in today's, I would say, celebration of computational science and in particular computational materials discovery. So with this, I want to start and tell you why we all believe that materials are very important to society. You know, materials really are at the core of key solutions for some of our core challenges, from energy and environment, but also support, as you all know, the development of the high-tech, high-value industries that characterize many developed countries, information and communication technologies, even healthcare, biocompatible materials. The materials properties of organic molecules of drugs are very important, down to fundamental science or experimental science being empowered by novel materials. To give you here, you know, just a few very quick examples. You know, let me, you know, show things that you all know and are familiar with, you know, starting from, you know, one of the first sort of modern smartphones. And here is Steve Jobs showing everyone the first iPhone. And, you know, this is all possible because of novel materials, from the transparent conductors that allow you to get away with a keyboard and having a touch screen instead, to the, you know, polymer lithium-ion batteries that can be made conformal to the shape of the telephone, to the, you know, ultra high efficiency piezoelectrics that can act as sound filters. And, you know, a couple of other examples, the nickel superalloys that sit beyond the combustion chamber typical modern jet engine don't melt because they have thermal barrier coatings that in a few hundreds of microns can drop the temperature by a couple of hundred Celsius, and that really means that you can run the engine as efficiently as possible without worrying about the blades melting. And this might not be a novel material, but I maintain that this is probably the most important material that has ever been found. And Fritz Haber, down in the corner, looking a little bit stern, together with his colleagues in the early 1920s, identified the iron-based catalyst that could make ammonia synthesis industrially viable. And the production of ammonia has been fundamental for two things. So one, that is not particularly good to make all the bombs of World War II and beyond, but also to make fertilizers that are really at the core, for better or for worse, of our capability of feeding close to 8 billion people. So these are just examples of materials. The way computational science enters into this is that these days we can predict the properties of materials without actually doing an experiment. And we go from fun projects like this one for the Swiss watch industry of predicting with quantum mechanical simulations, that is from first principle, as we say, the color of metal alloys or intermetallics, and you see that the top is what a computer tells you and the bottom is what an experiment tells you. But of course, a computational simulation is getting faster and faster and faster with the speed of information and communication technologies. So if you have the capability of predict materials properties, here we have seen the color, but maybe this is a bit more science oriented. This is predicting the resistivity of a monolayer of graphene as a function of temperature and doping. It also means that we can use a simulation to characterize and maybe even discover materials. So there was a couple of years ago this American publication, the Barron's Technology magazine, that said that today we are in the middle of a materials revolution because power simulation techniques combined with increasing computing power and machine learning are able really to automate the discovery process, vastly accelerating the development of novel materials. And this is exactly what I'm going to showcase to you today. And this is why Switzerland already, in 2013 decided to invest in a major center, what we call Marvel, on computational design and discovery of novel materials, with the idea that a number of principal investigators would work for 12 years around this grand plan. And this is actually one of the interesting scientific instruments for research in Switzerland. These are called National Center on Computation, on the Competence in Research. Marvel is one. Professor Kolmenberg, that will speak later, is actually involved both in Marvel and very much on a new one just created on catalysis. So maybe she'll mention that. But you see, because we had 12 years of funding, we could really sort of jumpstart an ambitious initiative in this direction. Design and discovery of novel materials, but also develop all the computational capabilities, the theory, the algorithms, the code, the digital infrastructure that made this possible. If you're interested in some of this, in the bottom left, there is our website, or I put here also some of the digital tools that I'll discuss in a moment if you want to know more about what we do. And I'll show here one example that is the discovery of novel low-dimensional materials like graphene that was exfoliated with Scotch tape from graphite by Gaim and Novoselov. And what we want to do in this project, or what we did, was really exfoliating, but not with Scotch tape, but with a computer, every inorganic material that is known. And low-dimensional materials are very interesting in general because physics and chemistry in two-dimensional, in one dimension, is very different from physics and chemistry in three dimensions. So there have, actually, these are just Nobel Prizes that have been given for physics or chemistry in two dimensions. And you see it goes from catalysis and earth to graphene, but also high TC superconductivity, or the anomalous Hall effect, or the giant magnetoresistance that powers all the spinning drive magnetic storage technologies. So what we do in a project like this, well, in Marvel, we have ingested all databases of known inorganic materials, and we have like 1 million different structures. And what we are doing is trying to figure out with the computer if these materials look a bit like this bottom left, that is, if they look layered rather than three-dimensional, like a piece of silicon. And if they look like this, we actually characterize with quantum mechanical simulation the three-dimensional parent, we call it, the two-dimensional exfoliated layer. We calculated those binding energy, we characterize all the properties, and we see if these are interesting. For this, we have built this open source infrastructure called AIDA, that is really a computational operating system to empower the capability to do thousands of calculations every day automatically. And this is just an example to show what we call a workflow in operation, where we take a material from our database, we characterize automatically all its properties, we do all the calculations to understand what is the electronic ground state, what is the geometry, what is the stability, and this is done day in, day out, without any human intervention. You know, we have built the capabilities to do this, and now this happens automatically. And for this material that you have just seen, you know, we save everything in this directed acyclic graphs, but also in databases that a human can explore. And if you were to go into the materials cloud in the Discover section, you would see many examples from the work of our groups, from the works of Professor Kolminberg and many other colleagues that, you know, expose to the world what we've done. So in this project, we started at the time with 500,000 different materials, and out of those, we identified a group of 108,000 unique stoichiometric materials, of which 5,600 of those were layered. So we calculated the binding energies for all of them, and actually 1,000 of those materials had binding energies that were comparable with graphite. So we really discovered all the known two-dimensional materials, from graphene to boron nitride to black phosphorus, the transition metal chalcogenides, but many, many others. And all this portfolio of new materials has a lot of interesting properties, from being magnetic metals, magnetic insulators, or semiconductors in one spin channel and insulators. This is all very good for spintronics. They could have very flat metallic bands, very separated from the rest of the bands. That is good for transparent conductor or plasmonics. They could be interesting with photocatalysis, but in the last 1 minute, I'll just showcase two of the searches that have been completed. One was to find materials that were two-dimensional topological insulator. This is what, by the way, the Nobel Prize to Haldane in 2016 was about. So materials that are insulating in the bulk, but they have topologically protected metallic states. And one of these was a material that was actually discovered in Brazil in 2008, made it to our database, and is a platinum-based mineral called jacutingate. And this was interesting enough that our experimental colleagues in Geneva made it, characterized it, and found the topological bands exactly as we had predicted. And the last one, and I'm concluding, is looking for new superconductors. This is tungsten nitride, one of the polytypes. And you see it's a material that has been very well characterized experimentally. It's beautifully layered, and our prediction is for a transition temperature of 22 Kelvin that would be the world record in 2 dimensions. So let me conclude that this is actually a project that has now concluded the discovery part. So we have exfoliated now actually the entire current 1 million database of structures. And what is ongoing is really the search for interesting materials. These are some of the core people that have been involved and driving this process. This is the group in Zoom time. And as I mentioned, you know, a lot of the funding and the jumpstart effort in this field has come from the Swiss Marvel project. Mainly Max and Big Map for us are core projects, and then support from many others. And with this, I thank you for your attention. Great pleasure to be here. Xie.
Thank you, Professor Mazzari, for the interesting talk. Now I'm delighted to introduce our second speaker, Professor Xingao Gong. He is a distinguished professor in Fudan University and also principal scientist of the major scientific research programs of the Ministry of Science and Technology, fellow of the American Physical Society and the academician of the Chinese Academy of Sciences. Professor Gong, the floor is yours.
Hello? Hello?
Yes, we can hear you.
Okay, good. Okay, thank you very much. And it's really my pleasure to join this interesting event. I'm very happy with my old friend, Nick Mazzani, and other friend, lecturers. I'm from Fudan University, and I'm based on this so-called key laboratory for computational physical sciences, Ministry of Education, and I think the audience from this from China all know this name, 教育部重点实验室. And also very recently we're going to have a new institute. It's called Computational Physics, Institute of Computational Physics, Physical Sciences in Fudan, and we are going to have a new building with the people from various kinds of departments like mathematics, physics, chemistry, and material science. All the people will come together in the same building. And what I'm going to tell you today is about this solar cell. And I think just Nick give a very nice introduction about the materials. And in his first slide, the first line is called energy harvesting. And this is the real solar cell to get the energies and from the sun. And I'll give you a very brief introduction on how the computational study understand the solar cell. And the solar cell is based on this so-called photoelectron effect, which was experimental invented maybe 200 years ago, and was explained theoretically by Einstein more than 100 years ago. Now this kind of solar cell becomes very, very, very popular. I think in last year that up to 5% of total electricity in China is almost from this solar cell. But you know, everybody knows that China is formulating an action plan for peaking the carbon dioxide emission before 2030. So there is a large development for this solar cell. People guess in maybe in next 20 or 30 years that the 30% of total electricity in China will come from the solar cell. So this becomes very, very important, and there must be a lot of research in this line. Actually, this solar cell, the physics principle is very it's not that complicated. You just need a very good materials with a very proper band gap between the VBM and the CBM, And as soon as you get there, I light to jump in, and you must kick off electrons from this VBM to the empty states, the CBM. And normally comes the electrons and holes will be recombinations. So the device must be well designed to separate these electron holes before the combinations. So as soon as you separate the electron holes and make an external load, and then you get efficient cell. So you can see the most important things you need very good materials to have these to absorb light and to have proper and the band structures in VBM and CBMs. So we have a one needed to design these systems to do this. So this is the usual solar cell structures. They need quite a few layers of materials, absorbers, buffer layers, and the window layers, and blah, blah, blah. So those layers must be well designed to have well prepare the band structures. This is the band structures, something else. And so these materials must be very good designed. So how can get this one? So one can use the first principle tools to design these kind of things. And one thing we have done here in this campus, so we designed the marginary semiconductors for acceptors. Why you may ask why marginaries? Okay, so because why marginaries, you have more elements and more flexible properties, and which could be possible for proper solar cell. Of course, sometimes some more elements will bring some more difficulties. If you look at the history of solar cell suburbs, they usually started from the silicon, these monomers, and then come to gallium arsenide or calcium telluride, and this is binaries, and then come to something like tenorates, blah blah. So the histories go from simple to complex, from monoray to the binary, tenorates, maybe why not quaternaries. So one can working on this. So how can go from simple to complex? So one usually since is using the element mixing, you making alloy. Suppose you start with the indium arsenide. So if we put the indium with the gallium, you put things together, you can see indium gallium arsenide. This is people call it mixing. You put the similar atoms together. So there is another way to do this is element mutations. This is so compound semiconductors. This way you can get new materials. If so, for instance, if you start with zinc and sulfur, if you place zinc with copper and gallium, so one atoms before the zinc in the periodic table, and the gallium and other atoms after zinc. So if you place two zinc with copper and gallium, so you get you do from the binary, you get these ternary systems. So you go further, you get from binary to the quaternary. For instance, if you start with sulfur zinc, you can get copper gallium sulfur. You can get, if you place two gallium with zinc and germanium, you will get the quaternary. So you do this. So you from simple to the complex, from the binary to the quaternaries. So you're not of choices. Of course, this is not that simple. You must use the first principle to confirm it, to get to get the structures. So this is what we have done. So people have done sometimes ago from zinc blank, you can get a clusterite and standard and some structures. So you can do it determined by the first principle. So what's the best materials for the absorber for the solar cell? So the calculation, so the simulation found these two systems. Okay, so is one of the best. Is one of the best materials for these best gap materials for the solar cell. So this is something like first the theoretical predictions, and then the experimental people found that this is really good. So this is example for the materials designs. I will give another one example for the solar cell. as I told you, this is the schematic showing of the solar cell. There's many materials, many layers they put it together, which is have a proper so-called band structures. So but the question is, what's the role of these buffer layers between the buffer layers and surface? Why is it needed? How it works? Why is it needed? So it is it's not well understood problems by experimental people. But experimental people say we just need this one. This is really necessary. But why they did it is not that clear. For instance, you look at these systems, calcium telluride. Calcium is one of the most important materials in the optical electronic devices. The band gap is something 1.5 electron is one of the best band gap for the solar absorber, which was known in 1970s. So at that time, people trying to do it for the solar cell, and up to 90s, they come to 16%. Now it's something more than 20%. It's one of the best the thin film solar cell, but from computational side, how can we understand it? So it's not so easy to do real simulations because these two systems have very large lattice mismatch. It cannot easily do in a real simulation by first principle. Because if you build a supercell, there's 2 million atoms from the first principle. So all solutions we need to do a neural network potential. Now it becomes very popular for the material science simulation, or one can say is one of the best example for the AI things in the computational material science. So we build this potential. We build this potential for these systems, for the calcium telluride on calcium sulfur, and build this potential and compare to real WASP potential first principle calculations. You can see this total energy difference is very small. So that means this kind of potential can be very good for these systems. So the point is how to build this as an interface model for the simulations. As I told you that the systems have a very large lattice match, and that means that they cannot simply put it together. So we built a model. So we are using 8 calcium telluride with this 8 unit cell of this calcium telluride. On this 9 unit cell of this calcium sulfide, and this lattice constant is quite similar. So that's in this case this lattice mismatch is not that big. So you can put these two things together, form these superlattice interface structures. So you can, in this case, you can do this to solid structures, but you just put these two things on together is not, of course, it's not that stable. You are we use the simulation annealing. That means you keep heating up this sample and see how the structure changes. Of course, if you see the energies, then if not change it smoothly up to some temperature, the energy drops down. That means the structure completely changed. So if you really from this high temperature, you cooling down, you will get this stable structures. In this case, you find the interface structure is quite interesting. At high temperatures, this could be in real observed this interface atom diffusion. For instance, the sulfur diffuse into the calcium telluride space. And generally, the structure is something that is a perfect position, the visions, and the position with dislocations. So it's like age dislocations. So it can be imagined. This structure is right. So in this way, we get this structure model for these systems from the with these AI potentials. As soon as we get these structures, you can one can really working on the other properties. So working to calculate or simulate why these systems is necessary. This buffer is necessary. So this is a way to solve the problems of real devices. And also, as one understands it, in the interface, there could be many defects. Now, in the previous model, we say these perfect systems there's no vacancy or interstitials. So how can one start this kind of things with defects? We use this differential evolution method and perform it at the interface regions. In this way, we can get these interface structures with defect. And with this, one can need to characterize the interface stabilities by calculating interface energies. So this is energy defined by this surface energy, interface energies, which is strongly depends on the chemical potentials of this of the elements somehow. That so we also do calculate chemical potential with the first principle and the neural network potentials, and one can see these AI potentials give very good results compared to defective potential of first principles. So what we can calculate this interface energies with these the AI potentials. So what do we get it? So it's for the interface energies. So if in most cases the systems prefer this neutral one, is without any defects. But for some cases, for instance, with the collision-rich places, they prefer some interstitials. With some interstitials, the surface energy becomes null. Of course, there is other cases. So this is in this way we can get these interface structures with defects, all right? And this is another systems. I don't know the dimensions. Okay, I would like to tell you one more thing for this. This is extremely important for the solar cell and the semiconductors. It's called defect-induced non-radiative combinations. And as I mentioned before, in a solar cell, as a night jump shut down, and you kick one electrons from the valence band to electron band. Okay, but as mentioned, for the effective solar cell, you must separate this electron hole before the combinations. So how long this knife, this electron hole pair? This is important. So usually in semiconductors, there's many defect levels. These defect levels will kill these electron holes. So one need to calculate, study this, how is the lifetime of the electron hole pairs. One need to very complex calculations. This kind of formulas actually is known 30 or 40 years ago, even, and which need to calculate the electron phonemes and lattice reaction. But to do real calculations is still is not so easy. So I'd like to show one last example, and for this quadratic semiconductors, we know this defect, zinc is replaced by tin. This defect is a bad defect. It's really that kills these kind of electron holes, which will decrease this efficiency of this solar cell. And is another most famous systems like ABX3. These systems recently is very popular in the solar cell systems. But we know these defects. The indium is replaced by lead. These defects also kill these key defects. And everybody knows that this one have very high efficiency. One can easily get something like more than 20% of efficiency. And the question for us is, why this guy is better than this guy? Why this guy is better than this guy? So we can easily calculate this capture rate. So we found that the capture rate for this in quadratic compounds is much higher than this in the ABX3 systems. So it's some 3 orders higher. So in these systems, if you jump in this electron from the V beam to the C beam, they can a larger rate to be captured. So that means that there's no output. So in that case, that's it's no very small efficiency of this cell. So in this way, we conclude this one could be good in some times. Of course, this is only explain why this guy have high efficiency, but these systems have another problems of the stability of systems. Okay, so I think I have shown you a few examples in which way we understand this solar cell by computational physics, we show that what can be done for the solar cell absorb materials design and the properties and our interface properties, which is very important for this solar cell, and the defects and the related properties of these capturing the electron holes, which could be play important role for the application of solar cell energies. Okay, so essentially this is what I want to show you most likely, and this is my cooperators, mostly supported by NFC of China, most, and Shanghai Municipal. Okay, thank you for your attention. I'll stop here. Thank you.
Thank you, Professor Gong, for the very informative presentation. Now let's welcome Professor Clemence Commonbuff. She's a full professor in theoretical chemistry at EPFL. She obtained her PhD degrees from the University of Geneva and then obtained her postdoc position at New York University and the University of Georgia. Okay, Professor Commonbuff, the floor is yours.
Thank you very much. If you stop sharing, I can then share, I think. Yeah, perfect. So thanks a lot. I will stick to my 12 minutes, so no worry on my side. So yeah, thanks for having me here. I think my talk provides a quite natural follow-up to the two previous talks, because I will focus more on chemistry and on molecular material. But the underlying theoretical framework that we all use is the same. It's what you have heard as being first principle, or here I call it quantum chemistry. And in my group, you will see an example later. We either resolve the equation explicitly, or we try to bypass the cost of the computation using a statistical learning model. Today, I will essentially focus on what we do with the theoretical framework in the concept of catalysis, because it's really one of the most important fields in chemistry and also in computational chemistry. And here is why. I mean, there's something you might not know. In Switzerland, you know that we export a lot of watches. Those numbers here are a few days old, but they are still, the trend are still valid. So as you can see, a few years ago, 25.4 million watches that were exported. No surprise, probably for none of you. But what is more surprising is that these shares of exportation is actually very small, less than 10%. And what Switzerland export the most, almost nowadays to 50% shares, is chemical and pharmaceutical products. And among these chemical and pharmaceutical products, 90% of them are synthesized using a catalyst. So that's really why the field is important. Especially in Switzerland, but everywhere. And that's also why computation played a big role in the field, as you will see. So even if you're not familiar with the field of catalysis, you are unconsciously an expert, because you will not be here without catalysis. For instance, the chemical reaction that occur in our body, they use big catalysts that are called enzymes, and they accelerate the reaction that will otherwise not happen in our lifetime. And another example that you're probably very familiar with is the catalysts. In this case, they are not enzymes, they are metal like palladium, platinum, or rhodium in the core. And what they do is they convert very toxic or polluted chemical like nitrogen dioxide in N2 or carbon monoxide into carbon dioxide to reduce the polluting emission from the core. So how does, if you don't know, how does a catalyst work? What's important to understand is that it doesn't change the starting material and the final product. So it doesn't do anything to the reaction, but it does change the path to one another. So we usually like to use the mountain picture. So without a catalyst, it will correspond to climbing a mountain to reach your final goal or your final product. With a catalyst, the path is going to be more complicated, but it's going to be much faster and much easier. So in a sense, catalysis will save for this reason time, energy, costs, and waste. So the different substances that we call catalysts and that will interact with the starting material can be enzyme. You saw an example before. They can be solids like those in the car, but they can also be molecular. And what we want to do in the lab, what we do in the lab is that we try to actually devise maps that are basically like geographical map. And this map, you can navigate on them to identify basically where are located, not the highest mountain or the longest river, but where you can find the most active catalyst or those that will be the safest, those that will be built with the most abundant transition metal and stuff like that. And once we are build those maps, we can then use them for large scale screening, 10 power 4, 10 power 5 or more. And this gives us really, this large scale screening enable us to really uncover trends that we will not be able to identify with a much smaller number. So which concept are we using? It's a concept that is valid in everyday's life, actually. Everything is a trade-off, and it comes from the Sabatier principle from 1913 that tell us that the best or the most active catalyst is going to be the one that that in a sense require the same energy for binding the reactor, the starting material, or for releasing the product. And if this energy is balanced, you then have an optimum catalyst. This principle was already used in solid state catalysis. What we did in a lab is that we exported it to molecular, or that's what we called homogeneous catalyst. So if you want to look at that in a more scientific way, you have many different possible paths that will be defined by the catalyst you use. And here you see that the green path is going to be the best because every step required the same amount of energy. The yellow path is not ideal because the first step costs too much energy and the last step is too easy. And the blue path is exactly the opposite. The first step is too easy. It's too easy to bind the starting material, but the last step, releasing the product, is too difficult. So basically all these different regimes, these different possibility can be cast thanks to the Sabatier principle into very simple plots that are called volcano plot for this kind, but there are many kinds. And those plots are very convenient because you then have a single descriptor that should be intuitive for chemists and that should be computable using those first principle approach or accelerated with machine learning techniques. And then you can categorize or classify the different type of catalysts leading to catalysts that bind too strongly, too weakly, or leading to really the optimum situation. So what we have been working on is basically to build many type of maps. Here you have several flavor. And this map, as you see the one in the middle, you can navigate on them and identify region based on those descriptors where the performance will be the best. So those maps are built based on those descriptors that we need to identify and that correlate with the catalyst performance. And once they are viable, you can really, as I said, couple them with statistical learning techniques to accelerate the navigation on those maps. So let me show you an example now, and this example will be about making carbon-carbon bonds. So here you have two small organic molecules that leads to a bigger organic molecule where the bond has been formed. That's the symbol for the catalyst. And in this case, those catalysts, they look a little bit like that. And if you see them as a Lego construction, you will understand that you can change the central piece, which is the metal, and what you attach to this central piece. There's another very important component that I'm going to call here the partner that you can also modify, and that leads to several ways to form a carbon-carbon bond. And this partner is very important because it actually leads to different category of reaction that are able to form those carbon-carbon bond that leads to really a lot of Nobel Prize. So now you might wonder, why do we want to make useless slightly larger molecule from small organic molecule, the answer is very simple. When you work with the food industry or the pharmaceutical industry or even the energy field, the molecule that you deal with, they become more and more tailored, more and more specific. And when you have this very specialized molecule, it becomes very difficult to actually selectively build or make a carbon-carbon bond. And here the bottleneck is really synthetic. So that's where computation can really take on the challenge. And what we have been doing is building those maps. That's what is called the genome of forming carbon-carbon bonds. So on this map here, if you navigate on the x-axis, you will have all the possible catalysts. If you navigate on the y-axis, you will have all the possible partner. And then you can actually see this plot as this three-dimensional version, and you can even cut some slice, and you go back to the different possibility that I showed you before that got different Nobel Prize. So now what you want to do here on the top, you see a handful of best possible catalysts, but if you want to screen a much larger number, we train machine learning model that can map a structure to a catalyst by training, in this case, kernel-rich model that is trained on a large database. And the outcome will be this famous descriptor that tells you if your catalyst is optimum or not. What we do then, once we do this large-scale computation, is what we deploy them on the Material Cloud, which is the platform for open science that is developed in Marvell. And then you get this interactive classification that you can see here, and that people can navigate through them. And the classification that we provide is actually based on the different metal and the different things that you attach to the metal. So they characterize the catalyst. And here you have an example where we identify 500 catalysts on the plateau region on the top, the black being the best. They are good for pretty much every type of reaction, and the gray, like for instance, silver, being good for nothing if you want to build or make a carbon-carbon bond. So when we work with industry, they sometimes want an additional criterion that is the price. So you can then refine this kind of search by selecting a subset of catalysts that are below, for instance, $10 per millimole. And that's what you have here. And that gives back a number that is smaller than that 500, which is 37 catalysts as you have here, with some with copper being the most active for this reaction. So that's an example to form a carbon-carbon bond. We have been building many type of maps for different type of reaction that are relevant to the field of synthetic chemistry. And if I just want to wrap up what we do, we devise those concepts or those maps that can be, that we can navigate on. We then accelerate the computation of the descriptor using those machine learning advancements. We deploy that on a platform for open science. And in this case, it was for catalyst screening, but we have apply a similar strategy for other type of molecular material. And with that, I would like to thank, of course, the funding and the group member. That's an old picture, but it's still semi-valid. And I would like to thank you for your attention.
Thank you, Professor Comenba, for the very interesting presentation. Now let's welcome our last speaker, Professor Peng Wong. He's a professor of uncertainty qualification at the Beihang University. He was awarded his PhD in computational science at the University of California, San Diego. He's also the co-principal investigator for the Chinese Material Genome Project in developing tools and a database for high throughput simulations and experiments for information storage materials. Now, Professor Wang, the floor is yours.
Okay, thank you very much. Let me share my screen. Okay. Okay, is it all? All right, okay. Well, late afternoon, thank you. And ladies and gentlemen, thank you very much for inviting me. My name is Peng Wong. I'm from Beihang University, and we are a very low-key university, not very well known outside China, except the American government, and which is not a thing we want to do. And our university is located in the northwestern side of Beijing. And we actually have a strong army of excellent researchers and a top 1% of students across the country. And also we are very good in engineering, in material science, physics, chemistry, electronic engineering, and aerospace engineering. So this is a brief introduction of my university. And also the last thing I want to say is my university is the best funded university in China in the last 5 years. And now I'll give a small brief introduction of my department. And our department is very young. We only founded 3 years ago. And the department, but we still maintain, well, even though our faculty is not as young as the department at 3 years old, we still maintain the youngest median age of researchers or faculty in the university. And we are also very interested in international collaborations. We already have dual degree with university in France and in Netherlands. And also we have collaborated with other universities around the world. And also we are lucky, very lucky to have Professor Albert Ferd, the 2007 Nobel Prize winner, as our adjunct professor, as our old guiding hand. And about myself, actually, I received my undergraduate degree at Durham University in the UK in mechanical engineering, and later on my PhD at the University of San Diego. After return to China in 2014, I first returned to the School of Mathematics and then joined the School of Integrated Circuit Science and Engineering in last year. And my research focus primarily is working on the development of uncertainty quantification tools and its applications. So in which our goal is to help domain scientists to provide efficient numerical tools or numerical frameworks to help them better predict stochastic system states or have a better design of their systems. And as the three professors have already demonstrated in the previously, so computation is a very powerful and ubiquitous tool in many fields, especially in novel material discovery. And so my team, we have also been working with researchers in material science, physics, chemistry, environment and energy, ecology, electronic design automations, and also drug product design. And today, I'll primarily focus on the design of drug product using the power of computations and via the works we have been doing with Pfizer research in the last 2 years. And the whole idea, the whole problem especially comes from the fentanyl crisis in the United States, in which people overdose of painkillers. And so this is a serious problem. And so most drug products right now adopt a structure of porous media, like the ones we see here. And so for those drugs, once it is usually designed in this porous structure, and they are embedded in these capsules. So once you take them in your stomach, they will gradually dissolve. And because the drug particles, they are embedded in a mixture of wax, insoluble wax, and poroformers. Once the whole drug into the body, it will gradually dissolve. And the drug particles would gradually come out of this porous structure. But in the design, in the manufacturing process, the harder part is usually the manufacturer can only mix the three substances: the wax, the drug, and the soluble poroformer into melt them together and into a liquid form. And with the liquid form, it will drop onto a spinning disk. And with this spinning disk, the whole drug droplet would travel along the tangent line and congeal along the way. But the only thing manufacturer can control is the composition of the three substances, but they have no control on the structure of the drugs. So one way we can do it is, of course, we use computational tools, and this would be to find a model between the local geometry L here and the global property, the effective diffusion coefficients of the drugs. But it is very difficult using direct computational tools. because first it involves a few multi-physics process. We have to, so we have solved a few coupled equations like Navier-Stokes equation, which is hard, and the transport equation, and finally we need to upscale them to derive the final D effective. And that is to do with one drug product, say with one microsphere. But usually these drug products, the capsules, contains hundreds or thousands of these microspheres. And we cannot know all the structure of these microspheres. So of course, this structural heterogeneity would render the whole effective diffusion coefficient uncertain. And our goal is to find a direct connection between the local geometry, the porous structure, and the effective diffusion coefficient of these hundreds of microspheres in a capsule. So to do this, instead of solving the whole equation, our goal is to build a surrogate model between the local geometry and the global properties. And in this way, we can avoid the curse of dimensionality, which is a prevalent problem in all computations. And to do so, of course, I mean, we can look at this picture. So when we, for example, when we scan a microstructure of a microsphere, and it will give us usually a binary image, and the image for a very simple case of only drug and or of only solid and fluid and pore, we can actually scan each pixel and put them into two categories. The white color, the white ball is pore, and the black one is actually the solid. But usually with these pixels, when you have a picture, you have thousands of pixels, and even if these pixels take only two values, binary values, either white or wrong, either white or black, you still have hundreds or thousands of dimensions. And this would actually render we cannot have that many features to describe a local structure. So instead, here we use Minkowski functionals to describe the geometric description of this porous network. And these four functionals describe the general microscopic case structure of the whole material. And once we have this, we can actually put them into the geometric characteristics for this whole geometry, and then build surrogate models accordingly. And here, actually, we can use generalized polynomial chaos, which is a popular tool in uncertainty quantification to build the surrogate model between the effective and the geometry. Or people could also use Gaussian process to build this structure and have a prediction on the D effective as a function of time. And so here we have a picture of these structures. And here we present the probabilistic density function, which characterizes the uncertainty of our prediction via 4 snapshots of the effective at time step 1000, 2000, 3000, and 4000. And as we can see, the blue histograms are the solution from 2000 Monte Carlo simulations, which take months to do. And the right dots lines are actually from our Gaussian process predictions. And as we can see, at all these 4 time steps, there's a good match between the prediction and these Monte Carlo simulations. But we're at a much lower cost because we only use 200 samples to build this surrogate model between local structure and the overall diffusion coefficients. And actually, with this PDF, with this probabilistic density function, one can conduct risk assessment, which by definition is the integration of the PDF over specific values. And once we build these surrogate models, it also enables these drug designers or the manufacturers to provide sensitivity analysis so that they can know which parameter exerts the largest impact on the probabilistic density function. So this way we can have a much better design for the drugs. So And these actually are a few references of the Minkowski functionals that we have been using and some of our own works relatedly. And lastly, actually, I would like to conclude. And so my talk actually will focus on provide a computational framework for drug product design. And this computation usually enables multidisciplinary collaborations between physics, mathematics, and pharmaceutical companies. And with these computational tools, it could also applicable to other fields. And here is the last of my talk. And I would like to take any questions. Thank you.
Thank you, Professor Wong, for the great presentation. Now is our Q&A session. We have received several questions from our audience. The first question is for Professor Mazzari. What are the most crucial things and key steps about predicting the real life using simulations? For example, in your color simulation, sometimes even with the best theories and the simulations, we still cannot predict the experiments. Could you comment briefly on this argument?
Yeah, that's a very interesting question. And indeed, that's where the competence of the scientists come into play. Because, I always say, first, simulation never fail. They just give you the wrong answer, and hopefully sometimes the right answer. And also there are things that we can predict very well and things that are much, much more difficult to predict. If you ask me, to predict how long it will take before the turbine blade will break, an incredibly difficult question because the time of breaking will come from a lot of statistical events and the complexity of the problem is really what we call a multi-scale problem. But if we look at the example of the color of a metal, that's a much clearer question for us computational scientists to answer. There are approximations. So for those of you that are expert in the audience, one has to decide if one describes electrons at the level of density functional theory or electrons at more accurate and more expensive level of many body perturbation theory. But it's a problem where we know almost all the steps and we can decide, the trade-off between accuracy and computational cost. But these days, if computational cost is not an issue, we can actually be very, very accurate. So really, it's a difficult question to answer because there are cases where our predictions we know already are going to be very, very close to the experimental results. And there are other cases where we can just give, good directions where to move. And in these cases, experiments are absolutely essential, but in almost all cases, the experimental verification and building of the material, the device is, the most important step.
Thank you, Professor Mazzari. And next question is for Professor Gong. It's about the fabrication. Once you have found a good material candidate, how do you work with the experimentalists to really make the material?
I'm a computationalist, and as soon as we have candidates for materials, I will just let the experiment people encourage them to synthesize it. Actually, in China, I have a few experimental groups of my friends. I will let them to do this. For this kind of materials, I'm working on these quarterly materials. They have a few ways to do this. One is by chemical and one by physical process. I say, yeah. This is what my answer. If it's not enough, I can tell you more. Okay. Okay.
Okay, thank you, Professor Gong. And next question is for Professor Kominbuff. What are the biggest challenge in your material discovery or modeling after your application of computational science?
But the biggest challenge is similar to the question that were raised by the other, to make sure that we can validate the prediction experimentally. And I think in chemistry, there's maybe a difference with respect to material science, is that, or not, I'm not sure. But the experimental chemists, they generally prefer that we try to reproduce what they do than the opposite by tradition and by habit. So we need to work, I feel, harder to convince them to try what we are actually predicting. And then the other challenge is to find all the concept that enable us to understand what makes an optimum material optimum. So what's the way to define that, which is not always as obvious for molecular material, for instance. We know the experimental target, but how to translate that into, let's say, a reward function that could be optimized computationally, it's a more complicated question.
Thank you. And the next question is for Professor Pong Wong. Since we have many problems to face today as a scientist, what factors will motivate you to start to design a certain material? For example, why do you choose drugs to research on?
Oh, well, actually, I was previously actually working with people in environment on soil, and because they are mostly porous structures, and as I was talking to a former friend working at Pfizer, and he said, well, that's actually the problem we are working on. And so he invited me to their work, and we discussed about what we can do with the design of the drug. And it was also a great actually learning for me, because that's how I see the difference between generic drugs and these original drugs. How the effect, their actually the impact or their effectiveness would differ because of the local structure.
Okay, thank you. And the last question is for our four speakers. Do you have any advice for young people who are very interested in material science? You can conclude in 1 or 2 sentences.
For me, I would say get a rigorous background in the underlying physics or chemistry, and add some knowledge on data-driven technology to that.
Thank you. And Professor Mazzari, do you have?
No, I absolutely. You know, always follow what you really love and not what is popular, because what will be interesting in 10, 20 years is not what is interesting now. And only by following what you love, you might, you know, find the road towards something that will be super interesting, not now, but in 10, 20 years.
Yes, there will be definitely a change. And Professor Gong, do you have any advice?
Well, it's I think it's the Nicola and Professor, how to pronounce her name, they have good suggestions. For me, I think for material science is a quite broad, very broad field, and many kind of materials. The materials what we are talking about today is most functional materials, and I think another material structures and other things. And the most important things once you are really interested in, what kind of materials are really interesting. Okay, if you need to for the future, if you want to work in materials, I think physics is a good topic, and you must have some. Yeah, I see. Okay.
And then Professor Wang.
Well, of course, I think you have to have a good background in material, in physics and chemistry. But I would also like to say computational material science. Of course, you need to do well in computation. In case one day you want to do something else, you can go also to other field with the computational tools behind you. Thank you.
Yeah, it's very useful, very potential. subject. Okay, due to time constraint, we have to end our session. And again, a great appreciation to Professor Mazzari, Professor Gong, Professor Kamenbov, and Professor Wong for your availability and your deep insights. And if you have any more questions, please send them to the email address on the slide. We will forward the questions to our speakers and give feedback to you. You're also more than welcome to scan the QR code to follow us on LinkedIn, WeChat, and subscribe to our newsletters. And thank you indeed for your active participation, and looking forward to meeting you in our next event. Bye-bye.
Bye-bye. Thank you. Thank you. Thank you.
Bye-bye. Thank you.
Bye-bye, Nicola. Bye-bye.